Imagine a massive, rigid structure violently shattering into dozens of smaller fragments, instantly bound back together by a tangled web of live wires. Microservices have become the default architecture for building large, scalable systems. Yet, despite their widespread adoption, they remain deeply misunderstood. A common entry-level trap is assuming that microservice architecture is achieved simply by writing and deploying small, isolated pieces of code. Complexity lives in the connective tissue, the way these isolated services relate, share data, and fail together as the system evolves. Splitting a system's code without carefully defining its data boundaries creates a distributed monolith. This yields a system that carries all the network latency of microservices with none of the independence, resulting in a fragile architecture that scales poorly. Building this correctly requires managing a specific set of architectural trade-offs to keep data consistent when the code is physically split apart. To see how this is done, we are going to build a resilient system from scratch using 3 specific patterns. Pattern 1, bounded contexts, Pattern 2, the integration tax, and Pattern 3, Saga choreography. Once you understand these patterns, the architecture stops feeling like a tangled mess of services and becomes a series of deliberate, defensible choices. Here is our baseline, a massive monolith holding billing, shipping, and inventory. The common mistake is slicing horizontally by technical layers, UI, logic, and database. This fails because a single concept becomes scattered across disconnected services that constantly communicate. Operationally, this creates a heavy, brittle coupling. A change to the database layer requires synchronized updates to the logic and UI layers, meaning one mistake breaks the entire chain. We solve this by slicing vertically instead, isolating business areas into separate silos, a bounded context. Architectural boundaries must follow the business, not the code. Inside, business logic and data move together, securely locked in a single silo. Organizationally, this gives engineering teams clean ownership. A dedicated team owns the shipping context top to bottom, with minimal overlap with billing. By keeping related rules and data physically together, bounded contexts drastically reduce the need for services to constantly communicate across the network. Looking at this layout, we now have 2 separate bounded contexts operating side by side, billing and shipping. To enforce true independence, we apply a strict rule, database per service. The primary advantage here is absolute isolation. Shipping can alter its data schema or switch engines without breaking billing, but this creates a hard restriction. The shipping service cannot directly reach into the billing tables. If a service needs outside data, it must politely ask the owning service via an API. Direct access is strictly prohibited. This strict isolation introduces a core architectural trade-off known as the integration tax. The first cost of this tax is the complete loss of cross-service SQL joints. To combine shipping and billing data, you must write extra engineering logic to merge it manually. The second, more severe cost is the absolute inability to perform a single centralized all-or-nothing transaction across those domains. True service independence isn't free. You pay the integration tax, sacrificing immediate, centralized data consistency. This poses a very difficult engineering problem. Without a single database commit, how do we process an order across order, billing, and shipping? This graph illustrates the solution, event-driven Saga choreography. To use sagas, you must abandon immediate consistency and accept a paradigm called eventual consistency. Eventual consistency means data across the system syncs up over time rather than in one instantaneous commit. Here's the choreography. The order service commits a local change to its database, then publishes an event announcing a new order. Other services independently catch that event, execute their local steps, and emit subsequent events, propagating the transaction down the line. The crucial defining feature of this pattern is that there is no central controller or master orchestrator. The system functions organically. Each node only knows its specific trigger and its specific output, reacting dynamically. Saga choreography pays the integration tax by distributing a single transaction across time and space. It maintains the correct sequence without sacrificing the independence of the services. Looking at the completed architecture, the system operates as a cohesive unit. First, bounded contexts cleanly align boundaries with business reality. Second, The database per surface rule enforces strict independence, accepting the integration tax. Finally, Saga choreography bridges these silos through continuous event cascades. Advancing to senior-level design requires a deliberate control over distributed data trade-offs, where every boundary is a conscious decision about what to sacrifice for independence.